So supposedly if we have two masses m1 and m2 separated by a distance r, the universal gravitational law states that the force of attraction between the two bodies is directly proportional to the masses m1 and m2, and it is inversely proportional to the square of the distance between them. Now, this force that is inversely proportional to the square of the distance is actually the inverse square law. And to explain the validity of this inverse square law, we tend to consider an observation. So the observation consists of a torchlight where this light illuminates the entire three-dimensional space that is available to it, and we place a photographic plate at a distance of 1 meter from the flashlight. So this photographic plate will be illuminated by the entire light, and the intensity of the light will be dependent on the total area of this photographic plate. Now supposedly, let's say we take this photographic plate and we take it at a distance of 2 meters. We find out that the total intensity with which the light covers this entire photographic plate will be 4 times the unit photographic plate. So this tells us that the amount of light will fade with a factor of 1/4. And similarly, if you take this to a distance of 3 meters, we find out that this entire photographic plate will cover a total area of 9 units. That means the entire illumination will result in the intensity being faded to the factor of 1/9. Now this relation of being from 1 meter and then 2 meters being 4 units and 3 meters being 9 units gives us a square relationship. And this is the same relationship we can extend for a torch. So if we have a torch and we make a spherical wavefront, the spherical wavefront with a surface area of 4 pi r square, we know that the area of the sphere is 4 pi r square. So if we increase the distance to let's say if we double the distance, we find out that the surface area, the amount of light incident on the surface area, it decreases with a factor of r square. Now this is the same concept which was taken by Newton, and he formulated it in a mathematical format. So in the 16th century, there were a lot of data that were collected by astronomers, and one such person was Johannes Kepler, who was studying about the orbiting planets. And in his Kepler's law, he mentions that the ratio of the orbiting distance of the planet to the star and the time period with which the planet orbits, so r cube upon t square, this ratio is constant. So Newton knew about the circular motion, and he formulated his own equations about circular motion, and he mentions that force is directly proportional to v square over r for an orbiting planet or for any sort of circular motion. So when v is directly proportional to r over t, we can square this velocity out. So this velocity, if we square it out, we find out we can actually incorporate Kepler's law into it, r cube over t square times 1 over r. And now once we have this value of v square, we can plug this equation back into our circular motion, force of circular motion, and we find out that the force is actually inversely proportional to 1 over r square, because r cube upon t square is constant. Now this is the exact thing what we needed, and this is how Newton was able to explain the inverse square law. Kepler, on the other hand, could not explain this phenomena, and this is where Newton was successful in proving the universal gravitational law and how it is dependent on the inverse square law format. And we see this inverse square law everywhere. It's a universal law, meaning that if we have two bodies separated by a distance r, if we double the distance, the amount of force of gravitation will reduce to 1/4. And so if we remove the proportionality constant, we have to replace it with a proportionality sign, and this proportionality sign is given by the gravitational constant. So F equals G times m1 m2 over r square. This tells you this is the universal gravitational law. And this similar law can be extended to other concepts as well, in electrostatics, in light sources, in photoelectric effects, and so on.